Welcome to Lesson 2.3 Jupyter Lab Setup. Learning Objectives. After completing this lesson, you will install Jupyter Lab for interactive development, create a proper notebook directory structure, configure Python kernels for your environment, learn useful Jupyter extensions, handle Windows paths correctly in notebooks. Why Jupyter Lab? Jupyter Lab is perfect for fine-tuning work because it allows you to run code cell by cell, great for experimentation, see outputs immediately, check model responses, visualize training metrics, loss curves, etc. Document your process, mark down cells, save intermediate results, checkpoints. Alternative. You can also use VS Code with Jupyter extension, but we'll focus on Jupyter Lab here. Installing Jupyter Lab. This command installs essential packages for running Jupyter Lab, which is a powerful interactive development environment for notebooks. By including IP widgets and IP kernel, you're ensuring that you can create dynamic interactive widgets and run Python code within the notebooks. When you execute this command, you'll see output indicating the packages being collected and downloaded. The successful installation message confirms that Jupyter Lab, along with IP widgets and IP kernel, has been properly set up. This step is crucial because it lays the foundation for your data analysis and machine learning projects, allowing you to leverage the full capabilities of Jupyter Notebooks. This command checks the installed version of Jupyter Lab on your system. Running it in PowerShell will display the version number in the terminal output. This step is important because it confirms that Jupyter Lab is correctly installed and helps you ensure that you're using a compatible version for your project. If you see a version number, you're all set to start using Jupyter Lab for your notebook development. If there's an error or no version number, it indicates that Jupyter Lab may not be installed and you'll need to address that before proceeding. This command is simply displaying the version number of Jupyter Notebook that you have installed. Knowing the version is crucial because it helps ensure compatibility with the libraries and extensions you plan to use. If you're following along with a specific tutorial or project, it's important to match the version to avoid any discrepancies in functionality. When you run this command, you'll see the version number printed in your terminal. If it matches the expected version for your course or project, you're good to go. If not, you may need to update or reinstall Jupyter Notebook to align with the requirements. Create notebook directory structure. This PowerShell script sets up the directory structure for your fine-tuning project. First, it navigates to the root of your project folder, ensuring that all subsequent commands operate in the correct location. The maki command creates several essential directories: notebooks, models, datasets, and outputs. The force flag allows the command to run without errors if the directories already exist. Next, it creates subdirectories within the notebooks folder, organizing your work into 3 distinct sections: setup, basics, and projects. This organization is crucial for maintaining clarity as your project grows. Finally, the script outputs a confirmation message in green text indicating that the directory structure has been successfully created. This feedback reassures you that everything is set up correctly and ready for the next steps in your project. This command outlines the directory structure for your fine-tuning project on Windows. Creating a well-organized folder hierarchy is essential for managing your files effectively as you work through the course. The Lessons folder will contain the course materials you've already received, while the Notebooks folder is where you'll store your Jupyter notebooks. Within Notebooks, you have subfolders for setup, basic training, and your specific projects, ensuring that everything is neatly categorized. The Models folder is designated for caching the models you will download, and Datasets is where your training datasets will reside. The Outputs folder will hold the results of your training runs, including checkpoints, which are crucial for saving progress. Finally, The transcripts and chats folders will help you keep track of video transcripts and documentation. This structure will streamline your workflow and make it easier to locate files as you progress through the course. This PowerShell command creates a write single quote .gitignore write single quote file, which is essential for managing your project's version control with Git. The write single quote .gitignore write single quote file specifies which files and directories should be ignored by Git. The code block lists various patterns to ignore, including Python cache files, Jupyter notebook checkpoints, large model files, IDE configuration files, and system files. This helps keep your repository clean and focused on the important code and data. After running this command, you'll see the message .ignore created in green text, confirming that the file has been successfully generated. This step is crucial for maintaining a tidy project and ensuring that only relevant files are shared with collaborators or stored in your repository. Configure Python kernel. Activating your virtual environment is the first step here, ensuring that any packages or dependencies you install are contained within that environment. This keeps your project organized and avoids conflicts with other projects. After activation, the next command registers your environment as a Jupyter kernel. The Python -ip kernel install command creates a new kernel specification for Jupyter, allowing you to select Python unsloth when you start a new notebook. The BSF flag installs the kernel for your user account, while MAME and display MAME set the kernel's internal and visible MAMEs respectively. Once you run this command, you'll see a confirmation message indicating that the kernel has been successfully installed. This means you're all set to use your unsloth environment in Jupyter Notebooks. Running the command Jupyter kernel spec list will display all the Jupyter kernels currently installed on your system. This step is crucial because it helps you verify that your Python environment, including the unsloth environment, is properly set up and recognized by Jupyter. In the output, you'll see a list of available kernels such as Python 3 and unsloth enviv, along with their respective paths. This confirms that both the default Python kernel and your specialized unsloth environment are ready for use. If you don't see the unsloth env listed, it indicates that the environment hasn't been correctly installed or configured, and you'll need to troubleshoot that. Your actual output will show fine-tuning, not unsloth m, and the path will point to Cecile users, user Abdada roaming Jupyter kernels fine-tuning. Both the Python 3 and fine-tuning kernels point to the same. Miniconda 3's tokens namevs fine. If you see your kernel listed, you're good. Launch Jupyter Lab. This code snippet first navigates to the notebooks directory where your Jupyter notebooks are stored. By executing the cd command, you're ensuring that Jupyter Lab will operate in the correct context, allowing you to access your specific notebooks seamlessly. Next, the Jupyter Lab command launches the Jupyter Lab interface. When you run this command, you'll see output confirming that Jupyter Lab has started successfully. Look for messages indicating that the server is running and that it's serving notebooks from your specified directory. The output will also provide a URL, typically starting with http://localhost 8888/lab, which you can use to access Jupyter Lab in your web browser. This step is crucial because it sets up the environment where you'll perform your fine-tuning tasks. Keep this terminal open. Closing it stops Jupyter Lab. Left sidebar, File Browser, Navigate Files, Running Terminals / Kernels, Manage Active Notebooks, Table of Contents, Document Outline, Extensions, Add Functionality, Main Area, Notebooks, your.ipinb files, Text Editor, edit.py files, Terminal, Command Line Access. Create your first test notebook. 1. Click plus, New Launcher. 2. Under Notebook, click Python unsloth kernel. 3. Rename. Right-click on untitled.ipnb true. This command creates a new Jupyter notebook file named 00-test.ipnb in the specified directory. The new item samlet is used here with the path parameter to define the location and the items file option to specify that we want to create a file. The force flag ensures that if the file already exists, it will be overwritten without prompting. After running this command, you'll see no output if it executes successfully, which confirms that the file has been created. This step is crucial because it sets up a notebook where you can start writing and testing your code. Once this file is in place, JupyterLab will automatically detect it, allowing you to open and work with it right away. Test notebook. Verify everything works. Copy this into your first notebook, 00-test.ipnb. Critical. Cell 1 must run before any imports. It sets an environment flag that disables TritonJIT on SM_61 hardware or run it out of order. Unsloth will crash when it compiles inference kernels. This code sets up essential environment variables for your Jupyter notebook before any imports. The first line disables the unsloth compilation process, which can help avoid unnecessary overhead during training. The second line turns off parallelism for tokenizers, ensuring that your tokenization process runs smoothly without potential conflicts. By printing the confirmation message, you're verifying that these environment flags have been successfully set. This step is crucial because it prepares the environment for the rest of your code, preventing issues that could arise from improper configurations. Make sure to run this cell first as it establishes the foundation for your fine-tuning tasks ahead. This code block is essential for confirming that your environment is properly set up for fine-tuning language models. It begins by importing necessary libraries including PyTorch and Unsloth, which are critical for working with large language models. The print statements provide a detailed environment check, displaying the versions of Python, PyTorch, transformers, PEFT, and TRL that you have installed. This information is crucial because compatibility between these libraries can affect your model's performance and functionality. Notably, the code checks for CUDA availability, indicating whether your system can utilize GPU acceleration. If CUDA is available, it lists the GPUs present in your system along with their specifications such as memory and compute capability. This output confirms that your setup is equipped to handle the computational demands of fine-tuning, ensuring a smoother training process. This code snippet is crucial for loading a lightweight version of the Qwen model specifically designed for testing purposes. The first step imports the necessary libraries, including the fast language model from Unsloth and PyTorch. The print statement indicates that the model loading process is starting, which helps track progress. The from_preprenoid method fetches the specified model, here unsloth/qn2.5-0.5b-instruct, and sets a max. The load_in_4-bit flag is particularly important as it optimizes memory usage, allowing the model to run efficiently on systems with limited resources. Once the model is loaded, you'll see a confirmation message. The subsequent lines check the GPU memory usage, providing insight into how much memory is allocated for the model. This output is essential for ensuring that your environment can handle the model's requirements without running into memory issues. Important: Tesla P40/SMN_61 limitation. The Tesla P40 is a Pascal architecture GPU, compute capability 6.1. Triton 3.2 generates PTX using the evict_first cache hint. Crash on the P40 asterisk because it triggers Triton GT compilation. Skip the inference cell in this test notebook. All training kernels work perfectly. Only the inference GT path is affected. For production inference, use VLLM cover in Module 5. This code snippet applies low rank adaptation or LoRa to your language model using the unsloth library. The write single quote fast language model.get_peft_model write single quote method modifies the model by specifying parameters like R, which determines the rank of the adaptation. The target_modules list identifies which components of the model will be adapted, ensuring that the changes are focused on the most impactful layers. The use_gradient_checkpointing option helps manage memory usage during training, which is crucial for working with large models. After applying LoRa, the code checks the GPU memory allocated, providing insight into resource consumption. The output confirms how many layers were patched, the number of trainable parameters, and the total memory used, allowing you to verify that your setup is efficient and ready for fine-tuning. What trainable percent 1.75 means: LoRa only updates 1.75% of all model weights. Instead of optimizing 502 million parameters, you update 8.8 million LoRa adapter weights. This is the core efficiency that makes fine. This code snippet is focused on freeing up memory before starting the fine-tuning process. First, it imports the garbage collection module, which helps reclaim memory by deleting unused objects. The Dell model tokenizer line removes these variables from memory, ensuring they don't take up space unnecessarily. Next, write single quote gc.collectSC is called to trigger garbage collection, and write single quote torch.cuda.empty_cache SCA clears the GPU cache, which is crucial for optimizing memory usage on your GPU. The output confirms that memory has been successful. The message all checks passed, ready for fine-tuning, indicates that your environment is now set up properly, making it a vital step to avoid memory issues during training. Model debugging with ELI5. ELI5 is a library for debugging and visualizing machine learning models. In this course, it serves two purposes: LoRa adapter inspection. Rank each adapter layer by its weight norm to see which layers are learning the most during fine-tuning. Token attribution. Highlight which input tokens most influenced A. Prediction. Useful for spotting dataset biases. This command installs the ELI5 library, which stands for Explain Like I'm 5. It's a useful tool for interpreting machine learning models, particularly in understanding feature importance and model predictions. By running this command, you're ensuring that you have the necessary dependencies to analyze and visualize how your model makes decisions. After executing the command, you'll see output indicating the installation progress, including the packages being downloaded and installed. Look for a message confirming that ELI5 has been successfully installed. This step is crucial because having ELI5 in your environment will help you better understand and communicate the workings of your fine-tuned model, making your results more interpretable and actionable. This also installs scikit-learn and SciP as dependencies. Add this as an optional cell in 00-test.ipnb. Run before cell 5 so the model is still loaded. This code snippet demonstrates how to use the ELI5 library for debugging and visualizing the behavior of a machine learning model, specifically a logistic regression classifier. First, it imports the necessary modules and checks that ELI5 is correctly installed by printing its version. This confirmation is crucial to ensure that the library is ready for use. In the first part, a synthetic dataset is generated with 100 samples and 4 features. The logistic regression model is then trained on this dataset. The explain_weights function from ELI5 provides insights into the model's feature importance, which helps us understand which features are influencing predictions the most. The output shows the weights for each feature, indicating their contribution to the model's decisions. The commented out section is for inspecting the norms of LoRa adapter weights, which is useful for understanding model adaptation, but requires the model to be loaded beforehand. Finally, the message confirms that the ELI 5 tools are ready for debugging, ensuring you can proceed with confidence in your model analysis. How you will use ELI 5 in later modules. Vertical bar use case vertical bar when vertical bar how vertical bar 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 coefficient weights vertical bar after training on classification vertical bar feature importance ranking vertical bar token attribution vertical bar during evaluation. Useful Jupyter Lab extensions. This set of commands is essential for enhancing your Jupyter Notebook experience. The first command installs the Table of Contents extension, which provides a structured outline of your document, making navigation much easier. Next, we install the Jupyter Lab Code Formatter, along with two popular formatting tools, Black and iSort. This ensures that your Python code is consistently formatted, improving readability and maintainability. Lastly, the Variable Inspector extension allows you to view all variables in your current session, which is incredibly helpful for debugging and tracking your data. After running these commands, remember to restart Jupyter Lab to activate the new features. You'll notice a smoother workflow and better organization in your notebooks. In Jupyter Lab, 1. Go to Settings through an Advanced Settings Editor. 2. Search for extensions. 3. Enable any you want. Jupyter Lab Configuration. This command generates a configuration file for Jupyter Lab, which is essential for customizing your Jupyter environment. By running Jupyter Lab Meetinas generate config, you create a file named write single quote Jupyter_lab_config.py. This file allows you to set various options such as default settings for notebooks, extensions, and server behavior. In the output, you'll see a message indicating the location of the newly created configuration file. This confirms that the setup was successful and you're now ready to modify the configuration according to your preferences. Customizing these settings can enhance your workflow, making it more efficient and tailored to your needs, so it's a crucial step in setting up your Jupyter environment. This creates ccell uses your name the Jupyter Lab config.py. This code configures your Jupyter Notebook server settings. Setting the IP to localhost ensures that access is restricted to your local machine, enhancing security. If you prefer not to have your browser open automatically when starting the server, you can set the open_browser option to true. The root_dir specifies the default directory where your notebooks will be stored, pointing to your fine-tuning project folder. Adjusting the iopub_data_rate_limit to a higher value allows you to handle larger notebooks without running into data transfer issues. Lastly, the token setting is commented out for security reasons. It's best to leave it enabled in production to prevent unauthorized access. After running this, you'll see confirmation messages in the terminal indicating that the server is ready with these configurations. Windows path handling in notebooks. This line of code sets the variable model_path to a hard-coded string that specifies the location of your model files on a Windows system. The path points to a specific directory where your fine-tuned model is stored. It's crucial to define this path correctly because it allows your scripts to locate and load the model when you run your training or inference tasks. Keep in mind that this path is specific to Windows and will not work on Linux or macOS due to differences in file path formatting. If you're planning to share your code or run it on different operating systems, consider using a more flexible approach like environment variables or configuration files, to handle paths dynamically. This code sets up the directory structure for your fine-tuning project in a way that's compatible with Windows. First, it imports the path class from the pathlib module, which simplifies path manipulations. The project underscore root variable defines the root of your project, either using an absolute path with forward slashes or a relative path that navigates up from your current working directory. Next, it constructs paths for your models, datasets, and outputs directories, ensuring everything is organized. The use of the division operator here is a neat feature of Parallel that automatically handles the correct path separators for your operating system. Finally, when you print the model underscore path, you'll see the full path to your model directory, confirming that the paths have been set correctly. This organization is crucial as it keeps your project tidy and makes it easier to manage your files during the fine-tuning process. This code sets up the directory structure for your Jupyter Notebook project, which is essential for organizing your files and keeping your workspace tidy. It uses the pathlib library to define paths for key directories, notebooks, models, datasets, and outputs. The loop ensures that these directories exist by creating them if they don't, which is crucial for avoiding errors later in your workflow. The get_output_dir function creates a specific output directory for each experiment, allowing you to manage results systematically. When you run the script, you'll see printed paths for the project root and each directory. This output confirms that your directory structure is correctly established and ready for use in your experiments. Having a well-defined structure will help streamline your work as you fine-tune your models. This code snippet is essential for setting up your Jupyter Notebook environment to access the necessary directories and resources for fine-tuning your language models. The first line imports the sys module, which allows us to manipulate the Python runtime environment. By appending the parent directory to the system path, we ensure that our notebook can locate the modules and files stored outside its current directory. Next, we import specific paths for models, datasets, and outputs, which are defined in a separate module named paths. This organization helps keep your project structured and manageable. The model underscore path variable points to the fine-tuned model, while dataset underscore path specifies the location of your dataset. Finally, output underscore path generates a directory for storing results of your experiment using a function that ensures proper. This setup is crucial for keeping your project organized and for easily accessing the files needed for training and evaluation. Jupyter Pro Tips: Vicars, vertical bar shortcut, vertical bar action, vertical bar, 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 shift plus enter, vertical bar, run cell and move to next, vertical bar, vertical bar, control plus enter, vertical bar A, vertical bar, insert cell above vertical bar, vertical bar B, vertical bar, insert cell below vertical bar, vertical bar DD, vertical bar, delete cell, vertical bar M, vertical bar, convert to markdown, vertical bar Y, vertical bar SA, tomato H, vertical bar, show all shortcuts, vertical bar. This code block is essential for enhancing your workflow in Jupyter Notebook. The first command, %time, measures how long the model takes to generate results, which helps you understand performance and optimize your code. The %timeIt command runs a function multiple times, giving you a more accurate measurement of its execution time, which is crucial for performance tuning. Next, %whos displays all variables in the current namespace, providing a quick overview of your workspace, which is particularly helpful for tracking your data. The %run command executes an external script, allowing you to modularize your code and keep your notebook clean. Finally, Enabling auto reload with %load_xt auto reload and %auto reload 2 ensures that any changes made to imported modules are automatically updated without needing to restart the kernel. This streamlines your development process, allowing for quicker iterations. This code snippet sets up a progress bar using the 2QM library in a Jupyter notebook, which is particularly useful for visualizing long-running processes like training models. The loop iterates through a range of 100, simulating a training process with a brief pause of 0.01 seconds on each iteration. The 2QM function wraps around the range, providing a visual indication of progress with the description training. As the loop executes, you'll see a progress bar that fills up, showing you how much of the task is completed. This feedback is crucial during model training, as it helps you gauge how long the process will take and whether it's running smoothly. This code snippet is designed to enhance the output experience in your Jupyter notebook during training iterations. The clear_output function from the IPython display module is called at the beginning of each epoch, which clears the previous output from the notebook cell. This keeps your output clean and focused, showing only the current epoch number. The loop runs for 10 epochs, and with each iteration, it prints the current epoch number in a user-friendly format. The wait = true flag ensures that the output is only cleared once the new output is ready to display, preventing flickering. As you run this code, you'll see the epoch number update smoothly, confirming that your training process is progressing without cluttering the notebook with repetitive output. This step is particularly useful for monitoring long-running processes in a visually manageable way. This code snippet defines a function to save your fine-tuned model and tokenizer, which is crucial for preserving your work and making it reusable later. The function save_checkpoint takes in the model tokenizer, the output directory, and an optional name for the checkpoint. It creates a directory for the checkpoint if it doesn't already exist, ensuring that your files are organized. The model and tokenizer are then saved to this directory, which allows you to easily load them in the future without retraining. After saving, a confirmation message is printed, indicating where the files have been saved. When you run the usage example in your Jupyter notebook, you'll see a message confirming the save location, which helps verify that your checkpoint was created successfully. This step is vital for maintaining your workflow and ensuring your progress is not lost. Common Jupyter issues. UHASI symptoms. Kernel restarts automatically. Kernel died restarting message. Causes: out of memory, code bug, seg fault. Solution: this code snippet is essential for managing GPU memory effectively when working with large models in Jupyter notebooks. The first 2 lines import the necessary libraries: PyTorch for handling tensors and GPU operations, and the garbage collection module to manage memory. The cleanup function is defined to free up GPU memory by first invoking write gc.collect_ac file, which forces Python to release unreferenced memory. Then write torch.cuda.empty_cache_ac file. It's crucial to call this cleanup function after loading your models to ensure that any unused memory is freed up, preventing potential out-of-memory errors during your training or inference processes. After executing this code, you won't see any output, but it confirms that your GPU memory is being managed efficiently, allowing for smoother execution of your notebook. This error message indicates that Python cannot find the unsloth module, which means it hasn't been installed in your current environment. This step is crucial because unsloth is the library we'll be using to fine-tune our language models. To resolve this issue, you'll need to install the module using pip. Once you run the installation command, you should see a confirmation message indicating that the package has been successfully installed. After that, you can rerun your notebook and if everything is set up correctly, the error should be resolved. This ensures that you have all the necessary tools to proceed with fine-tuning your models effectively. Causes: wrong kernel selected, package not installed in this environment. Solution: 1. Check kernel top right, should be Python unsloth. 2. Install in correct environment, Python # in notebook cell pip symptoms, fail to save error. Causes: file permissions, disk full, long file path. Solution: check disk space, check write permissions, shorten path if 260 characters. Jupyter Lab checklist. Mark off each item. Jupyter Lab installed. Pipe install Jupyter Lab. Neither directory structure created. Notebooks / models / datasets / outputs / Python kernel registered. Jupyter Lab launches successfully. Minas can create and run notebooks. Test notebook runs without errors. Minas model loads successfully in notebook. Inference works in notebook. Path handling configured using pathlib. Minus extensions installed, optional. All checked. Jupyter Lab is ready. Key takeaways: 1. Jupyter Lab is perfect for fine-tuning, interactive, visual, experimental. 2. Organize notebooks in directories. Keep projects separate. 3. Use palib for paths. Cross-platform clean. 4. Register custom kernels. Magic commands are powerful. %time, %whos, etc. 6. Clean up memory in notebooks. Call gc.collectAssay and torch.coda.empty_cache assay. 7. Save checkpoints frequently. Next lesson, Jupyter Lab is set up. Next, lesson 2.4, GPU verification notebook. In the next lesson, you'll create a complete GPU verification notebook that tests all your hardware capabilities, resources, Jupyter Lab documentation, NiPython, Jupyter keyboard shortcuts. This image illustrates the architecture of Jupyter Lab, which is essential for our work in this course. At the top, you see the browser frontend, which is the Jupyter Lab user interface where we'll interact with our notebooks. This interface communicates with the Tornado web server running at localhost on port 8888, which acts as the backbone of the entire application. Below the Tornado server, there are various kernels that allow you to execute code in different languages. The Python kernel, known as ipkernel, is the most commonly used, but you also have options for R and Julia, as well as Bash and SQL kernels, giving you flexibility in your coding environment. Additionally, the architecture connects to the file system, where your notebook's data and models are stored. This integration is crucial because it enables seamless access to your files while working within Jupyter Lab. Understanding this structure helps you navigate Jupyter Lab effectively and utilize its features to their fullest potential. Now that you have a grasp of the architecture, let's dive into setting up Jupyter Lab on your machine. This image showcases the anatomy of a Jupyter notebook, specifically how to structure your cells for model training results and code execution. At the top, we see a markdown cell that contains descriptive text outlining the purpose of this section, which is to summarize key training metrics like the loss curve and learning rate schedule. This is vital because it allows you to document your findings clearly, making it easier to compare results across different training sessions. Below that, there's a code cell where the actual model training takes place. Here, we import the necessary libraries and define the model using write single quote fast language model.fr preprimed followed by invoking the write single quote trainer.train.sr method to begin the training process. Remember that every line you enter here contributes to getting your. Finally, The output section gives you real-time feedback on the training status, showing the epoch number, current loss, tokens processed per second, and a progress bar. Understanding this output is crucial for monitoring your training process, evaluating performance, and making adjustments as necessary. As you move forward, ensure you take notes in your markdown cells to keep track of different experiments and outcomes. This will enhance your learning and help you refine your approach as you continue through the course. This image outlines the development workflow in Jupyter Notebook, which is essential for your fine-tuning tasks. You start by editing your code and tailoring it to your needs. After making your changes, you run the cell using Shift plus Enter. This step compiles your code and executes it within the notebook environment. Then, you will check the output to see if it behaves as expected. This feedback is crucial for understanding how your modifications affect the model's performance. Once you assess the output, it's time to iterate based on the results you observe. This iterative process allows you to refine your code continually, making adjustments as necessary to improve your model's performance. Mastering this workflow will significantly enhance your efficiency and effectiveness in fine-tuning large language models. Next, implement this process as you proceed through the course, ensuring you actively engage with your code and outputs. This image displays the recommended directory structure for organizing your fine-tuning project in Jupyter Notebook. Having a well-organized directory is essential for maintaining clarity and efficiency as you work through your experiments. At the top level, we have the main project folder titled Fine-Tuning. Inside this folder, there are several key subdirectories. The Notebooks folder is where you'll keep your Jupyter notebooks, with 3 separate folders for setup, training, and experiments. This hierarchy ensures that all relevant scripts are easy to find and run in the right order. Next, we see the data directory. Here you'll store your raw and processed datasets, helping you keep track of both original and clean data versions. The models directory is critical as it holds both your base models and any checkpoints, allowing you to manage different versions and states of your models. Lastly, the outputs folder is where you log outputs and results from your experiments. This structure will streamline your workflow, making it easier to navigate during the project. Now take a moment to set up this directory structure on your machine, as it will save you time and effort moving forward. This image presents the kernel configuration setup for your Jupyter notebook, specifically in the context of our course. First, you'll want to ensure you've created and activated your Python environment using Conda, which we've labeled here as fine-tuning. This environment is crucial as it will house all the libraries and dependencies necessary for your fine-tuning workflows. Once you have that environment ready, you need to install the ipkernel package, which allows Jupyter to use the Python environment you've set up. You'll see the commands for this at the bottom. You should type conda activate fine-tuning to activate your environment, and then pip install ipkernel to make sure the kernel is installed. After that, when you launch Jupyter, you'll use the Jupyter kernel selector to choose the appropriate kernel for your projects. In the drop-down menu, you should see the option for Python and Sloth, as well as the base Python version you're running. Understanding this configuration is vital because selecting the right kernel ensures your notebooks run with the correct Python version and libraries. Now, go ahead and set this up, and let's move forward to working with the Unsloth library in your projects. This image highlights some useful Jupyter extensions that can significantly enhance your workflow. Let's go through each one. First up is the variable inspector, which allows you to see all variables currently in memory. This is handy for keeping track of your data as you work through your code. Next is the execution time extension, which provides insights into how long each cell takes to run, helping you optimize your code's performance. The table of contents extension simplifies navigation in larger notebooks, making it easier to find your way through various sections. The code formatter automatically formats your code, ensuring that it adheres to coding standards and improves readability. Git integration is also invaluable, giving you version control features right within Jupyter. This means you can track changes and collaborate more efficiently. Finally, the LSP or Language Server Protocol extension offers powerful autocomplete and linting features, boosting your coding efficiency and reducing errors. Knowing and using these extensions will streamline your development process in Jupyter. As you set them up, you'll enhance your productivity and focus more on fine-tuning your models. Take some time to install these extensions and see how they fit into your workflow.